So, as you may have guessed from the title of my presentation, I'll be talking about functions with multiple versions. So what is function multiversioning? Function multiversioning is a feature that lets the compiler generate multiple function versions and auto-dispatch between them. Why would you like that? Because software is deployed on various devices, and we sometimes want to compile for a baseline architecture and then reuse the binaries on other targets. However, on most CPUs, we have optional instructions which may not be present on the target we are compiling for. For example, on ARM, dot product instructions may not be available. And to make use of such instructions, we need runtime checks. Right. So function multiversioning isn't new. It was introduced for the first time in 2014 for x86 using the attributes target and target clones. On those attributes, you could specify a string that corresponds to an architectural extension for which you would like to specialize your function on to be optimized for that target. However, on x64, the target attribute is mostly used as an optimization hint. And as you can see in this example, which is taken from the header files of ARM C language extensions, the target attribute is guarding a built-in. So therefore, we introduced a new attribute. We call it target version. And as far as I know, this has also been adopted by RISC-V. And we wrote a specification for function multiversioning. This is in ACLE, and it's currently in beta state. Right. Now let's talk about CodeGen. First, we generate multiple versions for a function, and to be able to differentiate between them, we want the features that each version is using to be encoded in the mangle name of each version. So if you see this example below, we have a version that is using 4 extensions of the architecture, CRC, BTI, AES, and BF16. And in the green box, you see what the mangle name looks like for this version of the function. Each of these versions is associated with metadata, and the reason we want them is to propagate information from source code to LLVM IR. Then you can imagine that when you have multiple versions of a function, you need to determine which one will be executed at runtime. And in order to do that, we want to detect which features are available on the host, and then from the versions that are available on that host, we still need to select the best version that is more suitable to execute. And to do that, we are using a priority scheme, which is part of the specification, and each architectural extension in the ACLE is associated with some priority. The resolution is being performed by a function called resolver function. This resolution is dynamic, meaning that it is performed at load time, and it is permanent for the lifetime of the process. And last thing we generate is a global variable to be able to store the state of the features that have been detected on the host. Right. So why do we need compiler RT? We need the runtime to be able to detect which of the features we're asking for are available on the host, and so that we can initialize the global state accordingly. This is supported across various platforms. And in this example, in the code you see on the left, we're looking at how this is done on Linux, where we ask the kernel using hardware caps which features are available, and then we initialize the global variable ARC64 CPU features. OK, now I hope this is visible. I'll talk about how to use functional multiversioning with an example to optimize your code. On the middle and the left side of the screen, we can see the source code, which I'll walk you through. And then on the right, we will see what the LLVM IR that is generated will look like, and I'll walk you through that too. So we have a program that takes two arguments. Those are strings. It concatenates them and writes them in a buffer. This buffer is then passed to a function called skipWord, which tries to identify white space, and then it returns the remaining string after the white space. We have two versions of skipWord. The one in the middle of the screen is the default. And on the left of the screen, we have an optimized version of skipWord for SV2 using inline assembly. And on top of that, on the top of the screen, you can see an auxiliary function called copyWord, which also has two versions. And those two versions are sharing the same body. And therefore, we use the target clones attribute for those. One is the default, and one is optimized for MOPS, which is an extension for memory operations. OK, so let's start looking at the IR. This is the codegen for the symbol that is resolved at runtime by the resolver function, which is associated with it. And you can see at the end of the line, we have one for copyWord and one for skipWord, because both are version functions. This is the mangled version of copyWord for MOPS with its associated metadata. As you can see, we have two types of metadata, which I'll talk into detail about them later on. One is the FMV features metadata, which is specific for multiversioning, and the other one is the traditional target features we have. This is the default version of copyWord with its metadata, the SV2 version of skipWord, and the default. And now comes the juicy bit, which is the resolver function. This is the resolver for skipWord. It does a couple of things. First, it initializes the runtime, which is the call you see on the first line, which we have to declare there. This initialization basically sets the global state, so the global variable ARC64 CPU features. On the second line, we read that global variable, and we compare it on the next line against a bit mask. And this bit mask corresponds to the SV2 version of skipWord. And depending on that comparison, we will select between the SV2 version of skipWord and the default. Right, let's talk about some design choices we had to make when implementing the spec. The first one has to do with the resolver emission. So we wanted to support functional multiversioning across multiple translation units. The challenge with that is that the resolver cannot see versions that exist beyond its current translation unit. And if you emit a resolver on use, meaning every time the function is called, you may have uses on different translation units, therefore multiple resolvers that are potentially different from one another. And why would they be different? Because maybe you declare different versions in each of the translation units. So the selection of versions would not be deterministic, and it would depend on the linking order. So I think the first object that comes to the linker is the one that will be selected. If you have two resolvers, the first one will be selected. So to deal with this problem, we decided to only emit a unique resolver in the translation unit where the default version resides. Another design choice had to do with feature detection. Specifically, we wanted to detect dependent on features transitively. So for example, if you have a version that is using SV2, you would also like to detect SV, the presence of SVE, the presence of FP16, and the presence of FP. And another case was that we wanted the features that are implied from the command line to not be exempt from runtime detection. Because in the example I'm showing you here with BTI, you may have an extension that is specified on the command line, but if it's not available on the host wouldn't trap when executing the instruction, but instead it would execute as no op. And if it did not detect it at runtime, you wouldn't know if it's present. And there were use cases where people wanted to just be able to detect features with multiversioning. OK, now I'll talk about roughly how we represent information for FMV in the compiler toolchain. The first thing we need is a name for the extension, so basically the string that goes in the attributes. Then we need a feature bit, which is what is used for runtime detection. This is part of the ABI. Another thing we needed is to be able to express the priority of FMV. So we do that with another entry there. And detection cannot be the same as priority. I wanted to highlight this. Because, as I said before, detection is part of the ABI, and you can imagine that in these enums, if you add or remove features, you would shift the values, and that would break the ABI. So that's why those entries had to be different, feature bit versus priority bit. Lastly, we want to store information about the architectural extension that corresponds to the multiversioning feature and its associated dependencies. And these dependencies are used for two reasons. One, to runtime detect, and then to enable the necessary sub-target features for code generation. And all this information, just to say that at first it was scattered here and there in the compiler, and you had to keep things in sync. And with the commit I'm listing there, we auto-generate this with TableGen, and it's easier to maintain. OK, and now let's talk about metadata. Why do we need them? How do they look like? Why didn't we use target features, which is very similar? So first, how they look like. They look like the red rectangle at that third line from the code. It's called FMV features, and then it's a list of architectural extensions separated by comma, lexicographically sorted, and unique. It's basically something more or less the same as target features. But I'll give you an example of why do we need them, and why did we not use target features. So imagine we have these two versions, the first one using i8mm and .product, and the second one using FCMA. Those are extensions for ARC64, in case you don't know. According to the specification, the priority of i8mm is higher, then FCMA comes second, and lastly, .product. Now, if we compile our program with mRC equals armv8 plus i8mm, this i8mm ends up being propagated to the target features, but for both versions. So at this point, we've lost information of where is this i8mm coming from. Is it coming from the command line, or is it coming from the target version attribute? So if we use target features to deduce the priority of the versions, we would think the second one has higher priority than the first, which is wrong. OK, here and for the next couple of slides, I'll be talking about an optimization in EuroLLVM, specifically in global opt. This is an optimization that allows us to statically resolve calls to version functions, meaning that we no longer have to perform runtime dispatch and resolve dynamically, but we can, at compile time, we can decide which version should be executed. This this can happen under certain criteria, of course, not for every call. And we do that by comparing the LLVM IR metadata between the caller and the callee. And we support two specific scenarios. The first one is when both the caller and the callee are function multiversioning functions, in which case we compare the FMV features between the caller and the callee. The second scenario is when the caller is non-FMV and the callee is FMV, in which case we compare the target features against the FMV features. So first, as you see on the left, what we need to do is to select which metadata we will use. And on the right, once we have selected the metadata, we construct a bit mask using those metadata. And with these bit masks, in the next couple of slides, I'll be showing you how we use them for the algorithm. The main benefit of this optimization is inlining. Right. So since global-op operates at the module level, we start by iterating the ifunc symbols in the module. The ifunc symbols is, if you remember from the second slide where I saw the codes in IR, it's the symbol that is generated for runtime dispatch. So we iterate over all the ifuncs in the module. We look into the associated resolver function for each ifunc, and we examine its basic blocks. We examine each basic block starting from the return instruction, and we walk backwards the useDef chain. As we iterate and through this process, as we walk through the useDef chain, we can recognize select instructions and fee nodes. And in any other case, we just bail. Once we have discovered all the callee versions, we use the masks I described in the previous slide to sort the callees in decreasing priority order. Next thing we do is we discover the caller versions. And again, similarly, we sort them in decreasing priority order. So now we've ended up with two sets of functions, the callers sorted in decreasing priority order and the callees. And here I will walk you through the algorithm with an example. This example is taken from the LLVM regression test suite. At the bottom of the screen, you can see the two lists of functions I just mentioned, the callers on the left, the callees on the right. The curly braces next to each version correspond to the bit masks. And in the node, I have added that there on the right, you see that those bit masks correspond to the features MOPS, SV2, SVE, FP16, and FP. That is simplified bit mask after dependency expansion. Another thing to note is on the top of the screen, you can see the red rectangle with the lambda function, which is describing the relationship between two bit masks. So when I say a bit mask implies another bit mask, it means that all the bits of the second bit mask are present in the first one. So you can also see two arrows here I have added. The red arrow is the iterator for the callers, and the green arrow, the iterator for the callees. So we can start the algorithm by comparing MOPS plus SV2 versus MOPS. So since MOPS plus SV2 implies MOPS, we can statically resolve this call. We advance the caller iterator. Now we are comparing MOPS versus MOPS. MOPS implies MOPS, so we can statically resolve this one too. And because of bit mask equality, we advance the call iterator. So at this point, we advance the call iterator because we know, since we are executing the SVE caller, we know that the MOPS caller that was higher priority is not present on the host. So we don't have to compare against it anymore. So now we are comparing SVE with SVE2. SVE does not imply SVE2 So we cannot statically resolve this call. However, because SV2 implies SV, we advance the call iterator. We keep skipping over callee candidates because, as I said in the previous step, the SV caller cannot be statically resolved. And since SV implies SV, we advance the call iterator once more. So now we are comparing both default versions. And since none of these features are available on the host, we can statically resolve. I hope it wasn't very complicated. On this slide, you can see some future work. One of those things is the user to be able to control feature priorities, and we have a pull request on ACLE for that. Another thing is the user to be able to refer to a specific function version. So we haven't decided how it would look like at the source level. There was an open ticket for supporting pointer authentication with iFang resolvers. And at the point of writing this presentation, there was a request to support more features like CSSC, which is some extension for pop count instructions. This has already been merged in post-LLVM 20 release, actually. And we would like you to use the feature because it's still in beta state, as I said. We need your feedback. We would like to see what's missing, what we would like to see. And lastly, I'd just like to thank all the colleagues who worked on this and who helped me with the code reviews. And now it's time for questions.
I'll start. Can your scheme be extended to support x86, for example, like AVX 512 has different newer instructions than previous AVX?
So the x86 implementation is already there, I think, since 2014, and it's separate.
Right.
So we did nothing on x86 implementation. Right. That's a separate thing.
Okay.
But there is support for it, I think.
Okay.
I don't know what the state of it is, but it is there.
Cool. Thanks. I guess there are no other questions. Yeah. Okay. Thank you.
All right. Thanks, everyone.